Okay, so we left off at the end of Wednesday. We started looking at that second definition of acid and base chemistry, the Bronsted-Lowry definition. And what we want to do in this session is we want to continue that discussion and also start to look at some of the calculations associated with this kind of field of chemistry, because there are a lot of different kinds of calculations that we can get into, and they can feel really complicated, but they're actually very related to each other. And so if we can pick up on the relationships, it'll make the calculations themselves a lot easier. So one thing that we kind of touched on and that we need to be a lot more explicit about here is this idea here. The idea that not only do we have the ability in a chemical reaction to identify acids and bases, but those acids and bases also have the capability of, if we look at the other side of the reaction, we can see that the other thing that is generated as a part of this reaction also has acid-base tendencies as well. And so we call those conjugate acids and bases. And so what we see is that they actually pair up with each other. In every acid-base reaction under the Bronsted definition, we will find these conjugate acid-base pairs, two molecules separated from each other by an H+ ion, either added or subtracted depending upon the behavior. So if I look at sulfuric acid, for example, H2SO4, H2SO4 acted as an acid in this reaction, gave a hydrogen to the water, and in the process became bisulfate, HSO4 -1, along with the hydronium ion, H3O+. Now, why do we call hydronium a conjugate acid and bisulfate the conjugate base? Well, because if we reverse this reaction, what we will see is that the behavior of each of these is the exact opposite of what they came from. Hydronium gives a proton to the bisulfate. Hydronium acts as an acid to form water again. Bisulfate acts as a base, takes that hydrogen, and turns back into sulfuric acid. It's acting as a base in that process. So in any acid-base reaction, we are going to see the formation of these conjugates. And the conjugate's behavior is always going to be the opposite of the original substance's behavior. So an acid is going to form a conjugate base. A base is going to form a conjugate acid. And I can always tell which two are which because I can look at the chemical formulas and see that they are only separated by a hydrogen. So let's take a look at this in a slightly broader form. I've got acids and bases and conjugates going on here. So if I'm looking at OCl and water, I can see the products here. OCl turned into HOCl. So what happened to it? Did it gain a hydrogen or did it lose a hydrogen? It gained one. Didn't have a hydrogen to lose. That's usually a telltale sign also. But since it gained a hydrogen, we know that it acted as a base. What does that mean for the HOCl here? It means that it is a conjugate acid because it was formed out of a base. I can look also and see that I have water and hydroxide. This is a conjugate pair. Water, in turning into hydroxide, gave away a hydrogen. So that's acid behavior, which makes the hydroxide a conjugate base. All right, let's look at the second example here. Here I have sulfuric acid and fluoride ion. Now, again, in this scenario, it's actually pretty easy to pick up on what the base is because an acid has to have a hydrogen to donate. There is no hydrogen in fluoride. So that's a pretty good sign that it's going to be the base, which makes HF its conjugate acid. And we have proof of that because we can see that the fluoride added a hydrogen. Adding a hydrogen is base behavior, not acid behavior. Sulfuric acid, on the other hand, we can see that it has lost a hydrogen. That's acid behavior, which makes the bisulfate its conjugate base. Now, for this last one, it's not as easy to see because both of the reactants have hydrogen. So it becomes a matter of, well, both reactants have hydrogen. How do I know which one is the acid and which one's the base? Well, here's where it helps us to identify the conjugate pairs. So I can look at this and say, okay, this one contains nitrogen and this one contains nitrogen. So they're a conjugate pair. What's the difference between them? Well, NH4 plus and NH3 are the pair. The difference between them is that the NH4 plus has more hydrogens, which means that it had to have lost a hydrogen to get to ammonia. Losing hydrogen is an acid behavior, which makes ammonium ion the acid and ammonia the conjugate base. My other conjugate pair is water and hydronium. We can see that the water has added a hydrogen. Adding a hydrogen is basic behavior, which makes the hydronium a conjugate acid. So the easiest way to go through this, honestly, is try to identify conjugate pairs from the problem, and then just identify how they're different from each other. In one direction or the other, the hydrogen had to be moving. If the hydrogen is being lost, it's an acid. If the hydrogen is being added, it's base. Any questions with this example? Okay, I wanted you to try this yourself. Here I have a reaction. I want you to identify just the acid and just the conjugate base. So identify which one of these is the acid and what its conjugate base is. So if you're not sure, at least try to identify the two different sets of pairs and see which pair is going to be acting like an acid and which one is going to be acting like a base. Okay, let's start by at least trying to identify the pairs. So HSO4 negative, what is its pairing substance? What is its conjugate? Sulfuric acid. Again, how do we know that? They're very similar in formula. They're only separated by a hydrogen. So that's one of my potential pairs. The other potential pair would be the water and the hydroxide, because those two, again, are only separated by a hydrogen. So those are my two conjugate pairs. We just haven't identified which pair is which yet. So we're looking for acid behavior. What does an acid do? Does it give away hydrogens or does it take them in? Acids give. So which one of those two reactants is losing a hydrogen? Water. The water is losing a hydrogen to turn into hydroxide. That's acid behavior, which means that it's the acid and hydroxide is the conjugate base. So for the purpose of the question here, that's what we were asked to do. Also importantly, we could identify then the bisulfate ion here as the base with sulfuric acid as its conjugate acid then. Weren't asked to do that in this particular circumstance, but certainly we could. So this kind of identification was at the heart of last night's experience, assignment. Any questions with this before we move on to more current affairs? Okay, so the bulk of the calculations, the bulk of the measurement that takes place with acids and bases focuses on the pH scale. And the pH scale is a calculated scale directly related to the concentration of the hydronium ion in solution. To calculate the pH of anything, I would take the opposite of the logarithm of the hydronium concentration. Now, why the opposite? Well, because hydronium concentrations are usually less than 1 molar in most aqueous solutions. And since they're less than 1 molar in most of those aqueous solutions, the logarithm of them ends up being negative. So we put a negative in front to turn them into positive values. So it's a mathematical reason more than any other kind of stylistic reason. We want pH values to be positive. This particular calculation would give us negative numbers unless we actually change them to positive by flipping this up. So if we know the concentration of hydronium, we can figure out the pH. Sounds easy enough. But obviously there are going to be some problems, because how do we know that value in the first place? And what if we're dealing with a base that has a whole bunch of hydroxide in it? How do I know the concentration of the hydronium? So the pH scale gives us the range of most common values for aqueous solutions, starting at 0, extremely acidic, all the way up to 14, extremely basic. And so at the 0 point of the scale, we have 1 molar hydrochloric acid. At the 14 end of the scale, we have 1 molar sodium hydroxide. If solutions were more concentrated than these, theoretically speaking, they would fall outside of that range of 0 to 14. We'd get up into either negatives or 14 and extra. But most solutions will fall into this 0 to 14 range. And your diagram here shows a variety of different products and things that you encounter in your home that fall within that 0 to 14 range. But there are a couple of things I want to really try to drive home here about this pH scale before we get into some more complex calculations. You can't see it from the seat. Hopefully you can see it on your phone or computer screen in Pear Deck. This big bar in the middle here gives us the concentration of the hydronium ion at these different pH values. So I want you to look at that and I want you to tell me how far apart is our hydronium concentration when you compare pH 8 to pH 9. The graph here says that the difference is 10 to the negative 8 for pH 8 and 10 to the negative 9 for pH 9. The difference between those is a factor of 10. And in particular, in this case, it's 10x smaller at that higher pH than at the lower pH. Now, what about if we go from pH 4 to pH 2? Now, on this part of the scale, pH 4 is 10 to the negative 4th. pH 2 is 10 to the negative 2nd. We are 2 factors of 10 different. So that's 10 times 10. So 10 times 10 is 100. And this time it's larger because our exponent is less, negative. Now, the reason I want to point this particular exercise out to you is because the pH scale is very easy to get confused on when it comes to a matter of what the scale means. Each tick up on the scale, either direction, represents a 10x change in concentration. And those 10x changes in concentration are multiplicative, not additive. So what I mean by that is, if I go from 4 to 2, it's not 10 plus 10 different. It's 10 times 10 different. So the difference is 100, not 20. And the reason that needs to be explained and said explicitly is because that's very easily confused. So this is a logarithmic scale. Every step on the ladder is 10 times greater than the step before it, or 10 times lesser than the step before it. So make sure that you're aware of that when you start comparing pHs and trying to figure out concentrations, because those steps are bigger than you think. Now, the pH scale and the values that we have come from that pH scale are based on a phenomenon of water called called autoionization. What does that mean? Well, in simple terms, what that means is that water in its great abundance actually can have the ability to act as an acid-base reaction with itself. And so if we think about those Bronsted-Lowry definitions, we can see that if water acts as an acid, it would create hydrogen. And if water acts as a base, it would create hydroxide. And we know from our extensive studies of water that water actually does do this to itself to a relatively small degree. What is that small degree? Well, that small degree is in neutral water, we get 10 to the minus 7th molar hydronium and 10 to the minus 7th molar hydroxide. If I take the logarithm of this, I get -7. Turn that negative into a positive, it's a pH of 7. So if you wondered why neutral water has a pH of 7, this is why neutral water has a pH of 7. Water does its own acid-base chemistry. And when it does, the resulting ions have the concentrations that put it right at the middle of that pH scale that was created. And so the other thing that we need to draw out of this is that for any aqueous solution, regardless of its acidity or its basicity, there is always going to be some amount of hydronium and some amount of hydroxide because of this autoionization. So even if I have the most acidic solution that I can think of, there's still going to be some hydroxide in it. And even if I have the most basic solution I can think of, there's still going to be some hydronium in there because of that autoionization. And that's why the pH scale doesn't very often tip below 0 or above 14, except in more theoretical kinds of cases. If I take that most basic solution that I can make, drop a pH meter into it, if it comes up above 14, it's not going to be considerably higher than 14. If I put it in that most acidic solution I can think of, it's not going to drop too far below 0. Autoionization is going to kind of stabilize it in and around 0 and 14. Because there's always going to be some amount of hydronium and some amount of hydroxide. Now, what if the solution is not at neutral 7 pH? Well, like I just said, if we're not neutral, we're still going to have some amount of hydronium and some amount of hydroxide present. They're just obviously going to be dwarfed by the one side or the other. So if I've got something that is acidic, it's going to be higher in hydronium and lesser in hydroxide. And as a result of that imbalance toward the hydronium, the pH is going to go below 7. The more imbalanced it is, the lower it's going to go. And similarly, if I have more hydroxide than hydronium, I'm going to see it tip over to the higher side of the 7 scale. It's going to go more towards the 14. The greater the imbalance, the closer to 14 it's going to be. And what this leads us to is because we have this relationship, we can actually put a number to it. The ion product constant of water, Kw, is always equal to 1 times 10 to the negative 14. Which is why we can say, regardless of how concentrated the hydronium is, there will always be some hydroxide because Kw is always equal to 1 times 10 to the negative 14. This particular equation establishes for us a relationship between hydronium and hydroxide where we can always calculate one given the other. So if I was interested in knowing the concentration of hydronium, but I only had the concentration of hydroxide, I would take 1 times 10 to the negative 14 and divide it by the concentration of hydroxide. And if I was interested in the concentration of hydroxide, but only had hydronium information, I could take the same 1 times 10 to the negative 14 and divide it by the hydronium concentration. There is a definitive relationship between these two concentrations. And with Kw, we know what the relationship is, and we can calculate to figure out what we don't know. So all this is showing is exactly what we just put on the last slide. Just how to manipulate this algebra to give us the relationship between the two concentrations. So let's take a look at some examples of these kinds of calculations that we can do. So with that example, if I have a table like this, it's actually really easy to figure out the concentration values because since we are only dealing with exponential terms, the division is actually a lot easier. So to find the hydroxide, I need to take 1 times 10 to the negative 14 and divide it by hydronium. Ten to the negative 14 divided by 10 to the negative 5th. If I put that in my calculator, it's going to give me 10 to the negative 9th. Now, how was I able to do that in my head? Well, because all the prefixes, the coefficients there are 1, it's just a matter of subtracting the exponents. So if I don't have 3 times 10 to the negative 9th, 5 times 10 to the negative 1st. If I just have the exponents, all I have to recognize is that the 2 exponents have to equal up to negative 14. And so in a case like this, this would be 10 to the negative 2nd molar. And on this side, it works just the same. 10 to the negative 14th over 10 to the negative 6th would be 10 to the negative 8th. And 10 to the negative 2nd here. Because again, if my coefficients are 1, then I just have to make sure my exponents add up to negative 14. I can just manipulate the exponents. Now, if I don't have that particular situation, let's just say for the sake of argument, we added a 5th line here. And this one had 3.1 times 10 to the negative 4th molar. How would I go about figuring out the hydroxide? It'd be the same thing. 1 times 10 to the negative 14th divided by 3.1 times 10 to the negative 4th. This one I would have to use my calculator for. And I would want to be really, really careful that make sure I'm using my scientific notation button. Because if you aren't in the habit of using that second E function or that exponent button, make sure that you use parentheses so that it doesn't divide by 3.1 and then multiply by 10 to the negative 4. You get a very different answer than what I'm going to get right here. 1 times 10 to the negative 14 divided by 3.1 times 10 to the negative 4. The two significant figures, 3.2 times 10 to the negative 11 would be the correct answer. If you're sloppy with your parentheses, or if you don't use the scientific notation button correctly, you might get an answer more like this. (3.1 times 10 to the negative 19). Very different answers. And the reason they are so different is because how did you handle this 10 to the negative 4? You're supposed to divide it. You accidentally multiplied it. That's an 8 degrees of magnitude difference. So you're literally talking about 100 million times more concentrated between the correct answer and the wrong answer. So make sure that you're using that calculator properly. If you're not sure what to do, come talk to me. I'll show you how to use your calculator for scientific notation, because it's been a month or so since we've had to do something like this. Right. Any questions with this? All right, to that end, let's go ahead and end up today with this question here. Here I'm giving you the hydroxide concentrations. I want you to turn them into hydronium concentrations. And so just remember, the relationship here is hydronium would be equal to Kw divided by the hydroxide concentration. So let's take this time. We've got a couple of minutes. Can you put them into your calculator correctly? Can you get the right answer? Can we interpret what it means in terms of the acidity of the solution? In both cases, we had to divide what we were given into Kw, into 1 times 10 to the negative 14. If we did that for the first one, we should have got 5.3 times 10 to the negative 7. In terms of answering the second question, acid, basic, or neutral, what we have to do is we have to compare which is more concentrated, the hydronium or the hydroxide. Didn't by much. The hydronium is more concentrated in number 1, so we would consider that solution to be acidic. Now, given that they're pretty close, it's going to be pretty weakly acidic, but it is going to be acidic. In the second case, do the same thing. We get 3.23 times 10 to the negative 13th molar for hydronium. In this case, the hydronium is considerably less than the hydroxide, so it's going to be basic. And again, given the magnitude here, we can conclude it's going to be pretty basic. So we're not going to see this material again until next Friday. Next Friday, we are going to do some more calculations related to this. We're also going to end with talking about something called a buffer. And that will close out chapter 14 for us, kind of ease back into it, because again, it'll been a week. So again, don't worry about post-lecture 14.2. We will cover that for next week. But make sure that you get that last participation point before you leave today. Have a great week, extended weekend. I'll see you next Wednesday for the exam.